Hi everyone! In this video, we will draw the mechanism which rotates the vertical stabilizer of Skylon. This mechanism is based on a push-pull linkage, similarly as what we used for the grid fins in the BFR booster. BFR booster, which has now been rebranded as Super Heavy by SpaceX. So, why do we need such a mechanism in the first place? Well, what we want to do here is to connect a servomotor to the vertical stabilizer so that we can rotate it 45 degrees in both directions. However, the airframe below the stabilizer is way too narrow to fit a servomotor at this location. This is why we will place the servomotor about 8 cm ahead of the stabilizer, where the hull is wide enough. Then, we create a linkage connecting the servomotor to the stabilizer. And this is where the push-pull comes handy, because it can transmit almost a pure torque. The components of this mechanism are first the servomotor itself, then a servomotor horn which is attached to the output shaft of the servomotor. Then we have a second servo horn which is connected to the axis of the vertical stabilizer. And finally, the two servo horns are connected using a pair of rigid links, creating a closed geometric loop. Now the rigid links are secured to the servo horns using pins, allowing them to rotate. Seen from above, the geometric loop created by the linkage has the shape of a rectangle, but it deforms as a parallelogram when the servomotor rotates. If you want to know more about how push-pull mechanisms work, I highly recommend that you watch the video How Does the Fin Move, and you will find this video in the playlist named SpaceX BFR Booster on this channel. As you can see, I first draw the mechanism in a separate file, and only then I insert it into the model of the ship. This avoids cluttering the screen with components that I do not need for the moment. Once I have drawn the mechanism, I insert it into the model of the ship and I check the dimensions. What I mean by checking the dimensions is, first, check that the servo horn connecting with the vertical stabilizer is actually aligned with the axis of the stabilizer. 2. Check that the servomotor has enough room to fit inside the airframe. And 3. Check that the mechanism does not come into contact with any part of the airframe when it moves. Next, we need to constrain the axis of the vertical stabilizer to prevent it from moving in undesired ways. The axis itself will be made using a metal rod 2 mm in diameter. Being attached to the push-pull linkage, the axis is already prevented from moving forward or moving backward. What we need to add are walls on this side of the axis to prevent it from moving left or right, and walls, or in this case I should say floor and ceiling, to prevent it from moving up or moving down. And of course, we need to leave enough clearance between the axis and the structure constraining it, otherwise it will not be able to rotate. Actually, since the plastic slightly shrinks during the 3D print, moving parts designed with zero clearance would just be impossible to assemble. I found that a 0.2 mm clearance between moving parts usually gives good results. And sometimes you will need some trial and error to find the perfect clearance. After that, we also need to cut out a slot in the vertical stabilizer to make room for the axis to fit. When I start designing a 3D model, the first thing that I have to decide is the scale. What should be the size of the final model? And the answer is always a trade-off. The bigger the model, the easier it is to place motors inside to actuate the moving parts. But since the build volume of the 3D printer is limited, the bigger the model, the more you have to slice it into small chunks to 3D print it. The smaller the model, the easier it is to fit it inside the 3D printer, but the harder it is to stuff motors inside. So for this specific model, a scale of 100 was the right size to do what I had in mind. But if, for example, I wanted to add a retractable landing gear, which I did not do for this time, the model would probably need to be 2 times bigger. So, does this mechanism work? Well, so far it's looking good. The stabilizer can rotate in both directions, so we can proceed to the next step. When you create this kind of mechanism, there is one more thing that you have to think about. How am I going to assemble it? If you are not careful, you might end up with something impossible to assemble, and depending on your personality, you might 1. Go back to the drawing board and rework the design. 2. crawl in fetal position and cry in despair, or 3. Throw your computer and half-assemble model through the window. I do hope that you would choose the first option. In this mechanism, there is a tiny screw that secures the horn to the axis of the vertical stabilizer. So to provide access to this screw, I cut out the last few centimeters of the tail, just behind the stabilizer axis. This makes it possible to insert a hexagonal key from the back of the airframe to tighten the screw. Of course, when you segment the airframe like this, you need to add structure to hold the segments back together. This is what I call a mating interface. In total, the airframe of this model is split into 7 segments. Now, to fit inside the build volume of the 3D printer, splitting it into 5 segments would be enough. But I need to be able to remove the tip of the tail and the nose to assemble the mechanism of the vertical stabilizer, which is located in the tail, and the mechanism of the canard fins, which is located in the nose. I hope you enjoyed this video. If you liked it, please don't forget to like, share, and subscribe.